Welcome to our lecture on the derivative as a function. So let's talk about what we know already. We have seen already that the derivative of a function at a point gives us the instantaneous rate of change of the function at that point. The instantaneous rate of change at a point is also the slope of the tangent line at that point. We now want to establish a function f prime of x, which gives us the derivative at any point, which is in the domain of f of x, all right, for which the derivative is defined. So we want to write a general equation this time for f prime of x in terms of x. So this would give us a generalized function for the derivative of the function f at any x in the domain of f. So it would be applicable at any x where that function itself is defined. So our definition of the function f prime of x is going to look like this. The derivative function f prime of x is the function which has a domain containing all x values for which this above limit exists. So notice that what's different this time is that we have generalized our definition of the limit definition of a derivative by replacing the a with x. And I'm talking about in this spot right here. So in example 1, we're going to use the limit definition of a derivative to find the function f prime of x, where f of x is this function here, the square root function. So first we're going to write down the definition. So here's our definition. And now we're going to substitute. So before we used a here, now we're going to use x. So we can form a generalized function f prime of x. Okay, so substituting, I'm going to get f prime of x is the limit as h approaches 0 of, in my function, I'm going to substitute x plus h for x minus f of x. So f of x in our case is the square root function divided by h. So in order to take that limit, we know that we've got to multiply by the conjugate. So we form the conjugate by changing the middle sign and multiplying top and bottom by the conjugate. So we carry out our multiplication. So by this point, we know that the two middle terms are going to cancel when we multiply by the conjugate. So we're just going to multiply the first and the last. So this is going to be the limit as h approaches 0 of the square root of x plus h times the square root of x plus h, which is x plus h. The radical comes off. And the last two terms are going to be negative radical x times positive radical x, which is going to be negative x. The radical comes off. And then we say we don't combine these two factors on the bottom. We want to see what cancels before we do any combining. So we have this. Now we can see that the x's are going to cancel in the numerator. So now we can go ahead and cancel the h as well. So we're just left with a 1 in the numerator. So we're going to say f prime of x is the limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. All right, so now we can go ahead and substitute 0, and we'll be able to evaluate this limit. So f prime of x is 1 over the square root of x plus 0 plus the square root of x, which is just square root of x plus square root of x in the denominator. So I have 2 square roots of x. All right, so this is f prime of x for the square root function. In example 2, it says use the limit definition of a derivative. So that's this definition. to find the function f prime of x, where our function is now x squared minus 2x. So let's do the substitution. So f prime of x is equal to the limit as h approaches 0 of substituting x plus h wherever I have an x in my function. So here is this one. Now here. So that's this substitution here. Now minus f of x itself minus this part here. So you got to be careful that you surround it with parentheses so you don't miss the distribution of the second term there. That's a common mistake. All right, so let's simplify this a little. Limit as h approaches 0. So we're going to expand this. Distribute the 2. Distribute the negative all over h. See what else cancels. So let's look and see what cancels here. Cancel here and here. Let's see. Cancel here and here. And then we've got the h, which will cancel now because I've only got, we'll go ahead and write that out, 2xh plus h squared minus 2h over h. So cancel the h here, 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 and here. So we can evaluate the limit as h approaches 0 now. So that would be the limit of 2x plus h minus 2. So I can substitute 0 in for h, and I'll get f prime of x. So this will go to 0 here, is 2x minus 2. So this is my function f prime of x, which is applicable to any x values for which the limit here, this limit here, exists. So let's try example 3. It says use the limit definition of a derivative, that's this, to find the function f prime of x, where this time we have a rational function. So let's set it up. So we're going to say f prime of x is equal to the limit as h approaches 0. Substituting x plus h into the function, I'll have x plus h plus 2, x plus h plus 3. So that's substituting x plus h into this x and to this x. Now we're going to subtract f of x, which is this function. And then we're going to divide by h. So let's put the h right here. That's the same thing as dividing by h. Okay, so we're going to simplify that. Let me make some room for that. So we're going to multiply in order to get a common denominator. So let me spread this out so we have some room to do that. All right, so I'm going to multiply this function here by x plus 3 over x plus 3, which is a form of 1. And I'm going to multiply this function by x plus h plus 3 over x plus h plus 3, which is a form of 1. Now we're going to have same, same. So we're going to distribute here, we're going to distribute here, and then we're going to create our new numerator. So let's go ahead and do the distributing. So we'll have x times x plus h plus 2, 3 times x plus h plus 2, and over here we'll have x times x plus h plus 3, 2 times x plus h plus 3. All right, so this is x squared plus, let's see, h times x plus 2x, 3x, 3h, 6. X squared, hx, 3x, 2x, 2h plus and 6. All right, so now we can get that all together and see what we have as a numerator now. And then we'll put the function back together. So we've got x squared plus hx plus 5x, combining like terms. That's all that. Now we got to apply this negative to all these terms. Negative. There's another 5x. Make that negative. Minus 2h minus 6. Okay, this is just my numerator. All right, let's cancel some. Whatever cancels here, 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 and here, here, and here. So I'm left with a 3h. There's a minus 2h. So this all is just h. All right, so that's my numerator. Now let's put this function back together again. So we've got the limit as h approaches 0 of my numerator over my denominator, which was here, these two, which I'm not going to go ahead and distribute. And then I've got my 1 over h right there. Okay, so now we can cancel the h's, and we're going to take the limit as h approaches 0 of 1 over x plus h plus 3, x plus 3. All right, so the h is going to go to 0. So that's x plus 3, x plus 3 on the bottom. So that's 1 over x plus 3 times x plus 3, which is the same thing as x plus 3 squared. Okay, so f prime of x is equal to 1 over x plus 3 squared for our rational function. Now, let's talk about notation. So there are some differences in notation when we talk about the derivative as a function here. So we've got the Leibniz notation. I'm not sure my German pronunciation is very good, but it looks like a slope dy dx. And then you've got Lagrange's notation, which is what we're going to use, which uses the prime, f prime of x or y prime of x, whatever your function is. And then there's Euler's notation, which is a d operator notation. There's Newton's notation, which instead of a prime uses a dot. So like I said, we're going to use the prime notation, which is Lagrange's notation, which is the most modern notation, the one that's more common these days. But you'll notice, as I did, that if you continue your study in any math-related field, you're going to encounter many of these different notations depending on your textbook, depending on your professor, and depending on the discipline. So they are there. There's a lot of different ones. So now we talk about how to graph a derivative. The derivative itself is a function, so we can graph functions. So let's say if we can graph a function f of x, then we should also be able to graph a function f prime of x. So if f of x has a positive slope at x, then of course f prime of x, which represents the instantaneous slope or rate of change at that x value, will also be positive at that x. If f of x has a negative slope, then f prime of x will have a negative value. So let's look at this example at the right here. F of x has a positive slope. So this is your function f of x, and you can see I'm going uphill from left to right. So I've got a positive slope. We call that an increasing function from left to right. So positive slope there. So if this is my graph of f prime of x, and this is my function that I could figure out, f prime of x, all of these values here are going to be positive values. They're not going to be all equal positive values. It's going to have a change in the magnitude of the derivative at each x value, and that's simply because the slope changes as you traverse along the function itself. It starts out very steep here, which indicates a high value for the slope, and then it gets to be more leveled out as you go this way, which means your slope is approaching zero, and you can see that happening with this graph here. We know that the slope of a horizontal line is zero. So if f of x, the function f of x, in this picture, this is my function f of x, has a horizontal tangent line at any of the x values along here, then we know that f prime of x is equal to 0 at that x value. So if I look over here and I figure out my slopes of my tangent lines as I go along this graph, when I get to the very bottom here at the vertex, the slope of that line we know is 0, which means f prime of x at that x value is 0. In this case, it looks like it's f prime of 1. All right, so the gold graph here, this orange or whatever, that one's f prime of x. So it's going to be 0. It's going to cross the x-axis at the point right here where the function has a horizontal tangent line. So this is one thing that really helps us a lot when we're trying to graph the derivative function, the first derivative, or any derivative for that matter. The places where you have a horizontal derivative, you're going to intersect the x-axis and x-intercept. So this last bullet point here says the slope of f of x will be 0, where the graph of f of x transitions between increasing and decreasing, or you could say it the other way, between decreasing and increasing. So here I have a downhill slope, negative slope, and then right here at this point where I go horizontal, it transitions to being a positive slope. So that's what this is saying right here. So for example 4, we're going to try to sketch the graph of f prime of x on the same set of axes as the graph of the function f of x. So what we said before was one of the things we can pick out pretty easily is where you're going to have a horizontal tangent line, and that's where you transition from negative slope to positive slope, or in this case here, you're going to transition from positive slope to negative slope. Okay, so right at these values right here, if I'm graphing my f prime of x function, it's going to cross right there where I've got a horizontal tangent line. So I've got two graphs for my function f prime of x already. All right, now I know that if the slope over here is negative, then the graph of f prime of x is also going to have a negative value, which means it's going to lie down here somewhere. It doesn't necessarily mean it's the same negative value, but it's going to approach from the negative and eventually hit 0 here. Just a rough idea. Now, if I look after that, from here to here, I've got uphill, 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 all the way to here. The values of my f prime of x are all going to be above the x-axis. They're going to be positive numbers, and then they're going to have to swing down and hit 0 again there. So there's going to be some shape here. This is fairly constant right here. But at some point in here, we call that an inflection point, and we deal with that a little later. You're going to have it, you're going to reach the highest point of your positive slope, and then you're going to have to bend over. Let's just try to sketch that in, and eventually get back down here to 0. So there's got to be some kind of a bend and a peak that occurs in here. And that occurs at this inflection point right here, where you where you hit your maximum, your highest positive slope, and then you start to bend over and approach this horizontal slope, which is a zero slope, represented by this dot down here. So this is just an estimate. All right, so I'm here. Now I go from zero slope to being negative slope again, so that means I got to be down here somewhere. And notice it gets fairly linear at this point, which means I'm going to level out at some sort of a constant value. So I'm just estimating right now, but it is going to have some leveling out that goes on. So this is my f prime of x rough sketch on the same set of axes. We've got our signs right at least, but not necessarily the magnitude of the slope. The zeros are correct. We know it's basically going to have that kind of a shape. So let's try it again. This time we have a slightly more complicated graph maybe. So I'm going to look at it carefully. So I'm coming downhill, so this is negative slope. Then I level off here. At some point it's zero slope. And then I'm negative again. I'm still going downhill here. Then I level off here. I've got a zero slope. And then I go uphill. So this branch of it over here, this part of it is positive slope. So if I'm graphing f prime of x, of course this is f of x, I know I'm going to have a dot here where the zero slope is, and a dot here where this zero slope is. Okay, those are dots on my f prime function. All right, so then I know I'm negative. All of these are downhill, so I got to be down here somewhere, eventually hitting zero. So down in there somewhere, rough sketch. All right, so then I can see here that I'm negative here as well. Negative, 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 negative. So all of this is negative in here, approaching back up to zero. So something's going to have to turn around in here somewhere, which means there's an inflection point in here somewhere where I change directions. So I'm going to go just roughly back up to zero again. All right, then the last piece from here on over, this is all positive slope, and it gets fairly linear, so it looks like it's going to level out at some certain value. All right, so starting to level out. All right, so that's a rough sketch. We've got the signs correct, we got the zeros correct, but I may not have the magnitude correct. I got the basic stuff correct. All right, so we just wanted a rough sketch. Okay, now we got to discuss continuity. So derivatives and continuity. So we're going to say if f of x is differentiable, that's the word that means you can take the derivative of f of x at some value, x is equal to a, then f of x is continuous at x is equal to a. There's not a whole jump or anything like that, or an infinite discontinuity, or an asymptote. That's the same thing. All right. Then we say if f of x is continuous at x is equal to a, then f of x may fail to be differentiable at x is equal to a for several reasons. All right. So it doesn't go both ways. If it's differentiable, it's continuous. But if it's continuous, it's not always differentiable. Not always. Okay, then we say, if f of x is differentiable at x is equal to a, that means what we're saying is that this limit must exist. There are several cases where this limit doesn't exist. So let's first investigate when the limit does not exist for certain cases because f of x is simply not continuous. All right, so it's discontinuous. So things that we know already are discontinuities, are places where you have a vertical asymptote. So here, you're discontinuous here. So the derivative will not exist at that value in that picture, it's at x is equal to 3, right there. Okay, and then at a jump. So here you've got a jump. So your derivative is not defined at x is equal to 3 in that diagram there. So then you've also got a removable discontinuity which could occur. So that would be a hole. Let's draw one. So let's say you had a hole right here, or removable discontinuity. Your derivative would not exist at that hole, at that x value. In that case, x is equal to 1. So now, there are certain cases that exist where you do have a continuous function. Here's two examples here. These are both continuous. And you can tell because you don't hit a hole or a jump or an asymptote. Now they are continuous, but the derivative doesn't exist in certain cases. In this graph, we have this corner here, this sharp peak. All right, if you have a corner, the slope coming into it this way from the left is different than the slope coming into it this way. So that means that the left-hand limit and the right-hand limit do not equal one another. So therefore, this function, the limit does not exist when you have a peak. And that's because you're coming in at two different slopes from the left and the right. All right, so that's this bullet point here. At a corner or a cusp, f of x is definitely continuous, but it's not differentiable because there's no tangent line at that corner or cusp. You're coming in this way, you're coming in this way, but you never meet at one tangent line at that peak. All right? So the slope is different from the left and the right. All right, so then we've got this case over here where the graph of f of x has a vertical tangent line. So you come in here, and then at some point right here, your tangent line to the curve is actually vertical. All right, and then you slope off over this way. All right, so that's like an inflection point there. All right, when you have a vertical tangent line to the curve, where it has a point where the curve goes vertical, then we know the slope of a vertical line is undefined. So therefore, this slope, f prime of a, is undefined for this vertical tangent line here, right? And the derivative does not exist. So these two cases here, they are continuous, but still they're not differentiable. Example 6 says, determine the x values where the derivative does not exist and state the reason why it does not exist. So we're going to say this is our function f of x, and the domain of f of x is from x is equal to negative 6 to x is equal to 4.5 over this span right here of x values. All right, so first let's look for the places where we're discontinuous because the function f of x itself is discontinuous. All right, so that's going to occur here at x is equal to negative 4. And then we have another discontinuity here at x is equal to 2. And then we have another discontinuity here. We've got a removable discontinuity at x is equal to 4. Okay, so the derivative f prime of x does not exist. Let's just say does not exist because the function is discontinuous at these x values here. We'll just call them x is equal to a. So let's just say this particular function doesn't have all of the types of problems. It doesn't have the cusp. It doesn't have the vertical asymptote issue. So you could see other reasons why. This is just, in this example, there's just these 3 x values where the function happens to be discontinuous, and therefore the derivative doesn't exist. Now let's talk about higher order derivatives. So since we've established that the derivative is a function itself, f prime of x, we can take the derivative of that function, since it is a function, in order to obtain higher order derivatives. So that means f double prime of x is the second derivative of f of x. It's the derivative of the first derivative. It's the derivative of f prime of x. And we could keep going. F triple prime of x is the third derivative. It's the derivative of the second derivative. And the second derivative is the derivative of the first derivative, etc. So we could keep going if we wanted to. So there's some certain special higher order derivatives that we work with a lot. The position function, s of t, position as a function of time, like with the ball problem that we've done before. S of t indicates the position of the object at time t. V of t is the derivative of s of t, and we call that the velocity function. We've seen this one before. And then a of t is the derivative of the velocity function, which is the second derivative of the position function, and this is called the acceleration function. So these come up a lot in calculus. So in example 7, we're going to find the second derivative. So we're going to find f double prime of x of this function f of x is this, using the limit definition of a derivative. So first we're going to find f prime of x. So we're going to eventually find f double prime. But first we're going to find f prime of x using the limit definition. So let's write that down. So here's the limit definition. So I'm going to substitute. So this is going to be the limit as h approaches 0 of substituting x plus h for x plus h for x, then subtracting the function, which is 2x squared minus 3x plus 4. All right, so that's my numerator. So this is all over h. So let's simplify the numerator. So that's 2 times expanding the binomial x squared plus 2xh plus h squared minus 3x minus 3h plus 4 minus, let's fix that 4, minus 2x squared plus 3x. I'm distributing the negative, and that would be minus 4. All right, that's just my numerator there. So let's go ahead and finish simplifying the numerator, then we'll put it all back together. So this is 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 4 minus 2x squared plus 3x minus 4. So what can we cancel here? 2x squared, 4, 3x. So that leaves us with 4xh, 2h squared, minus 3h in my numerator. So putting it back together, I've got f prime of x is equal to the limit as h approaches 0 of 4xh plus 2h squared minus 3h all over h, where we can now cancel the h. So we're going to take the limit of, as h approaches 0, of 4x plus 2h minus 3. All right, so that means I'm going to substitute 0 for h, so I'm left with 4x minus 3. So we found f prime of x, which is equal to 4x minus 3 using the limit definition. All right, so now we want to find f double prime of x, which is the derivative of f prime of x, which is the limit as h approaches 0 of f of, let's just go ahead and substitute it right in here. So we've got 4 times x plus h right here, minus 3 minus f of x, which is now 4x minus 3 all over h. So simplifying that, we're going to have, let's look at the numerator, 4x plus 4h minus 3 minus 4x plus 3. Cancel, 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 cancel. So that's just the limit as h approaches 0 of 4h divided by h, which now the h's will cancel. So the limit is simply 4. So f double prime of x is equal to 4. We finally did it. So we found f double prime of x by differentiating f prime of x. So let's do a couple application problems here. The position function for a particle moving along an axis with time is s of t, where position is in feet, time is in seconds. Find the velocity and the acceleration functions. So this velocity function is s prime of t. The acceleration function is s double prime of t. And evaluate them when t is equal to 2. All right, so let's go ahead and find s prime of t first. So s prime of t is the limit as h approaches 0 of this function right here. So we've got 3 times t, we're using t instead of x, plus h squared minus 2 times, t plus h plus 1. And then we've got subtract the function itself, 3t squared minus 2t plus 1. So that's my numerator. So this is all over h. We'll put it out front. We're now going to simplify that numerator. Let's expand this out. H squared minus 2t minus 2h plus 1 minus 3t squared plus 2t minus 1. All right, so there's some more distributing here. Let's finish this. 6ht 3h squared minus 2t minus 2h plus 1 minus 3t squared plus 2t minus 1. All right, so something should cancel in all this. So the 1 minus 1, negative 2t plus 2t, negative 3t squared, 3t squared. So we've got 6ht 3h squared minus 2h over h. So s prime of t is the limit as h approaches 0 of 6ht plus 3h squared minus 2h divided by h, where now the h will cancel. So we've got 6t plus 3h minus 2. So I'm going to take the limit as h approaches 0 here. So this term will go. So we have 6t minus 2. So that means my velocity function, v of t, which is the derivative of the position function, is 6t minus 2. So we've got that now. Now we want to find the acceleration function, so we have to differentiate v of t. So a of t is equal to v prime of t. So we've got the limit as h approaches 0. Now I'm working with 6t minus 2, so I've got 6h plus t minus 2 minus v of t itself, which is 6t minus 2, all over h. All right, so let's get this simplified. So in the numerator, I've got 6h plus 6t minus 2 minus 6t plus 2. Cancel, 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 cancel. So I've got 6h over h. So a of t then is equal to the limit as h approaches 0 of 6h over h, where the h's now cancel. So that would just be 6. So a of t is equal to a constant 6. So we wanted to evaluate the velocity and the acceleration at t is equal to 2. So we're going to substitute 2 into the velocity function. So that means v of 2 is equal to 6 times 2 minus 2. That's 12 minus 2. That would be 10. V of 2 is equal to 10. And then a of 2, since it's just constant, it's always going to be 6. So a of 2 is 6. Now the units, let's put our units on. The units for velocity would be, is it feet or meters? Let's see, do we have feet? So feet. Velocity, feet per second. And then acceleration, 6 feet per second squared. Feet per second squared. Units for acceleration, feet per second squared. Okay, so those are our answers at evaluating the velocity and acceleration at time t is equal to 2. Last thing we're going to do is the ball problem again. So we have a ball dropped from a height of, that should say 84 feet here. Oops. Okay, let's do our last problem here. This is the ball problem, the ball dropping problem. So we've got a ball dropped from a height of 84 feet. So its position above the ground is given in feet, where here's your position axis, and here's your time axis, time in second, position in feet. And this is the shape of the curve. This is your curve. It's a parabolic curve, upside down, quadratic, where position, we said the position is in feet, time is in seconds. The questions are, let's highlight them. What time does the ball hit the ground? What is the instantaneous velocity of the ball when it hits the ground? And what is the average velocity during its fall? So let's answer the first question. What time does the ball hit the ground? So what we mean is, what is this time right here when the height is at 0? Okay, so that means we're going to set the height, s of t, the position, s of t, equal to 0, which means negative 16t squared plus 84 is equal to 0, which means 16t squared is equal to 84, or t squared is equal to 84 over 16, which I can reduce 42 over 8, or 21 over 4. So if I take the square root of that, I'll get t is equal to root 21 over root 4, so that would be 2. All right, so this is our time when the ball hits the ground. So that answers the first part. This time over here is root 21 over 2 seconds. Next, we want to find what is the instantaneous velocity of the ball when it hits the ground. So right here, the instant it hits the ground, how fast is the ball moving? So we need to find v of t, the velocity function v of t. So that's the first derivative of the position function. So that's the limit as h approaches 0 of using the function, substituting into the function h plus t squared plus 84 minus the function itself, which is negative 16 t squared plus 84. This would be all over h. All right, so let's simplify that numerator there. So that's negative 16 h squared plus 2ht plus t squared plus 84 plus 16t squared minus 84. So we can cancel the 84s. Do this distributing here. 16h squared minus 32ht minus 16t squared plus 16t squared. All right, this is still the numerator. Cancel, cancel. So now I can put the h back here under these two terms. Cancel, cancel, cancel. So now v of t is equal to the limit as h approaches 0 of negative 16h minus 32. So substituting 0 in, this is going to go to 0. So we're left with negative 32. So the velocity function is, wait, what happened to my t? This t is right here, is negative 32t. So I have a new function, my velocity function, which is the first derivative of my position function. So now we can substitute the time that it hits the ground to find the velocity of the ball when it hits the ground, now that we have the velocity function. All right, so v of root 21 over 2 is equal to negative 32 times root 21 over 2, which is equal to negative 16 times root 21 units of velocity, feet per second. Okay, so this is the velocity as it hits the ground. Okay, so the last part of the question is what is the average velocity? So we want to find the velocity at time t is equal to 0. We know the velocity at the end of its flight when it hits the ground. We want to find the average of those two velocities. So we'll plug time t is equal to 0 into the velocity function, and you can see what that's going to be, 0, right? So v of 0 is equal to negative 32 times 0, which is just 0. All right, so we're going to take the average of, let's call it the average velocity. So that'd be v of 0 plus v of whatever that time was, the end time, and divide those in 2. So this one's actually just 0. So we've just got the velocity at root 21 over 2 seconds, which we know is 16 times root 21 over 2. So our average velocity is just half of that, basically, which is negative 8 root 21 feet per second. And this is our average velocity. So that ends our video for 3.2. So I hope you took good notes, and we're ready to try the practice problems now.